All right. Well, thanks everybody for joining us again today. We have a lot of ground that we'll cover in today's presentation. Here's a brief overview of some of the topics we'll get into, but really the intent behind today's information is to get you guys up to speed with HVLS fans, how to properly size and specify them, and then at the end of the talk here today, hopefully feel confident in making a product selection and putting a product on your fan schedule. So we'll start off for anybody who is a little bit newer or less familiar with HVLS fans with just some very, very high level kind of basic information. I always like to start off with just what is an HVLS fan. These are relatively new products in terms of the rest of our industry. These fans have only been around for about 20, 25 years. So they're still kind of a little bit new and still a lot of, I guess, new applications that are being discovered for this type of product. But what is it? What does HVLS stand for? HVLS means high volume, low speed. And essentially that name tells you exactly what this product is. It's a large diameter ceiling fan that is intended to circulate high volumes of air, the high volume part of the name, at relatively low operational speeds. So that's the low speed part of the name. And to put that in perspective for you, when we're talking high volumes of air, you may be thinking, 30, 40, 50,000 CFM. We're actually looking at much larger volumes than that with this type of product. So a 24-foot HVLS fan can move upwards of about 250,000 CFM. And again, for some perspective on what we mean by low speed, that same fan can move that much air at about 60 RPM. So again, much lower operational speeds than maybe you're used to with a traditional exhaust or supply fan type of product. So I mentioned that, with these products being relatively new, there's still a lot of applications being discovered for them. So to give you guys, again, a feel for just generally speaking, where are they used, there's a lot of different types of buildings and a lot of different applications that we're seeing these products in. Their bread and butter, their kind of main niche is more in the industrial space. So warehouses, manufacturing facilities, wastewater treatment plants, anything where you have potentially an unconditioned building that a lot of people are, performing some sort of work in, and we need to provide them some creature comfort to keep them active, keep them productive in their job. But there are a lot of other applications that are becoming more and more prevalent for HVLS fans. And these are starting to get into more of the commercial and the institutional side of the market. So educational facilities, they're a great product for moving or distributing air in large open spaces like gyms, auditoriums, cafeterias, retail spaces, and commercial buildings. Again, really good fit for different types of areas in those buildings where you have a lot of people congregating or perhaps a large open space with a tall ceiling. Government buildings and life safety buildings, so police stations, fire stations. And then there's also a pretty good fit for this type of product in agricultural facilities. So whether that be, an indoor grow facility, we've seen fans in barns for dairy cows to try to keep the cows comfortable and productive. There's a lot of different places that this type of technology can be applied. And the reason why we're seeing them become so widespread in all these different types of applications is because of the different use cases for HVLS fans. So there are a lot of reasons why you might use this type of technology, but there's really four primary ones that we'll talk about in a little bit more detail throughout the presentation today. And those are a few of the things that I hinted at on the last slide. Number one, the probably overwhelming majority of reasons why an HVLS fan is used is to increase thermal comfort and occupant productivity in these different types of spaces. So again, if you have an unconditioned space that, we need to move some air and help people feel more comfortable in, or even if you have a conditioned space that maybe we just need to improve the air distribution, air circulation to keep people comfortable, that's really the primary use case for an HVLS fan, is to circulate that air and improve that, that occupant's feeling of comfort in the space. But there's some other use cases that are, again, becoming more and more common. Reducing building costs is a big one that we'll spend quite a bit of time on later on. HVLS fans are very effective at reducing not only your upfront installation costs for an HVAC system, but also your long-term ongoing operational costs. We can use this type of product to help maybe reduce the need for some other air distribution equipment, or we can also offset the operating costs of some of that other HVAC equipment by taking advantage of this fan's ability to circulate high volumes of air. They're also very effective for improving indoor air quality and occupant health and safety within a building. We can help break up some stagnant areas within a facility where you might have, contaminants starting to pool up, and we can also help, keep some unwanted bacteria and mold and things like that from growing within a space. And then last but not least, we're starting to see a pretty big push for this type of product purely for the architectural design element of these fans. Believe it or not, we've actually sold several fans into projects where the fan will never run. It's just purely there for the impact and the wow factor of seeing a 24-foot diameter fan when you first walk into a big space. So a lot of different use cases. And again, we'll go into each of these in detail over the remainder of the presentation. So starting with that first application, thermal comfort and occupant productivity. Again, HVLS fans are very effective at providing what I like to call creature comfort for people in a space. So there's two primary mechanisms that are used to do this. The first is that because these fans are very effective at circulating such large volumes of air and basically turning the air in a facility over at a very high rate of speed, we can use them to help distribute air a little bit more evenly in a space. So you may be familiar with the term de-stratification. That's the process of breaking up thermal gradients that naturally occur because of warm air rising and cold air settling in a space. And these fans are very effective at breaking those thermal layers up and getting a more even distribution, a more uniform temperature from floor to ceiling in a space and from side to side in a space. So the graphic I have on screen is one example of what that looks like. If you have a conditioned space that's heated, naturally over time, especially if you have a very tall ceiling, that warm air is going to start to rise and that cold air will start to settle in the space. And you get what you see on the left side of that graphic, a pretty large temperature disparity between floor and ceiling. And in some cases, this can be upwards of 20 to 30 degrees, depending on the height of your building. So this is a pretty extreme example that we're showing here, but has been observed in actual applications. If we put in an HVLS fan and we have that fan circulate that air and again, turn the air over in the space, what we're able to do is get a more even distribution of temperature from floor to ceiling. You will still likely see a few degree offset between floor level and ceiling level, just because the fan is constantly combating that natural rise of warm air. But we get a much more even temperature distribution. So maybe a couple degree difference from floor to ceiling versus that 20 or 30 degree difference. So that's one example or one mechanism that's used for thermal comfort. The other is that the fans are actually able to provide elevated air speeds for occupant cooling in summer applications, or again, maybe an unconditioned application that has no air conditioning equipment. So basically you can think of this like the fan providing a breeze across somebody's skin. It's not actually cooling the air in the space, but by providing that airflow, that air movement across their body, we're able to make them feel a certain amount of temperature offset or a certain cooling effect based on just evaporation of sweat off of their skin. So it's a very effective way to provide, again, that creature comfort, particularly in unconditioned spaces. But there's also some advantages in a conditioned space to perhaps reduce the amount of air conditioning that you're supplying and using the fans to provide that additional level of perceived cooling effect. So with that thermal comfort being, the primary mechanism or the primary application for why you would use an HVLS fan, it's really important that we have a good methodology for defining what comfort is to an occupant. And luckily, there is an ASHRAE standard, ASHRAE 55, that does exactly that. It defines a methodology for quantifying the impact of air movement on somebody's comfort in a space. So there are a lot of variables that play into occupant comfort that the standard defines. Airspeed is probably the most critical of those. So like I mentioned on the previous slide, elevated airspeed across somebody's skin will make them feel a bit cooler, even if we're heating a space. But temperature, relative humidity, the metabolic rate of an occupant, or really how much work, how much output are they doing, and how much heat are they generating from their body, as well as the clothing level of occupants. Are they wearing a long sleeve shirt like I am today or a short sleeve shirt? Those all affect occupant comfort. And really what ASHRAE 55 is trying to do is define a set of parameters given some of these inputs that will make majority of people in a space feel thermally neutral. They're not cold, they're not hot. That's really the end goal that we're looking for here. So here's just an example of what that looks like in practice. This is a widely available public tool that was developed by the Center for the Built Environment at the College of Berkeley. So you can search this in Google, or I have the link at the bottom of the screen there if you want to use this tool. But this basically allows you to run scenarios or different simulations of the comfort level that somebody would experience in a space given those variables that we discussed previously. So I can input the temperature of the space, the amount of air speed that I'm providing to the space with an HVLS fan or other equipment, relative humidity, the metabolic rate, and the clothing level of my occupants. And then this will help me determine if I'm providing that thermally neutral environment or if an occupant would feel warm, hot, cold, or cool. So I have two scenarios inputted here. On the left-hand side is with a 20 feet per minute airspeed. On the right-hand side is with a much higher airspeed, 150 feet per minute. And what you'll see in the comparison here is that on the left-hand side, that low airspeed condition with my temperature, humidity, and those other factors inputted, I actually have a slightly warm space. So occupants in this area would be slightly uncomfortable versus the scenario on the right, scenario number 2, with the elevated airspeed provided by an HVLS fan, I have a thermally neutral condition. So occupants would feel, in this case, comfortable as defined by the ASHRAE 55 standard. So this is a really good tool that can be used for determining if an HVLS fan is a suitable solution for a given application and what the impact of that elevated airspeed might be. And I'll make a quick, kind of comment about Greenheck's software here. If you're familiar with our CAPS or eCAPS software, these exact same equations, the exact same, scenario building that we have here is also available in Greenheck's CAPS and eCAPS software. So if you're making a selection in those software packages, you can run this directly in CAPS and eCAPS without having to leave and go to this College of Berkeley tool. So thermal comfort, obviously, probably the most important, the most critical application, but that thermal comfort feeling is very closely related to occupant productivity, which for a building owner, this is really kind of the end goal here, right? Is we want to make sure people are comfortable in the building so that their productivity level, their ability to do whatever it is that they're doing in that building is maintained. So a lot of scientific studies have shown increased productivity when that thermal comfort is maintained in a space. And surprisingly, to probably nobody in this call today, most studies find that peak productivity occurs between 70 and 72 degrees Fahrenheit, which is why most of you are probably designing to those conditions in a lot of the spaces that you work in. That's shown in this graph on the right-hand side of the screen here. The temperature axis is in Celsius, just for full transparency. But if you do the conversion, that peak of the curve is right around that 70-degree range. But additional studies have also found that there's about a 1% productivity loss on either side of that roughly 70-degree temperature range for every 1 degree of discomfort that somebody feels in a space. So what you can see is that if we start to get into scenarios where somebody is extremely uncomfortable, maybe they feel like it's 10 degrees too warm or 15 degrees too warm in a space, there can be some pretty significant productivity loss there. So again, I'll use the same example of an unconditioned warehouse. If it starts to get up into the 80s, 90s, 100 degrees inside that warehouse, there can be a pretty substantial drop off in the output level of workers in that space. So the Small Business Bureau estimates that this is roughly a $5,000 savings from keeping occupants, keeping employees comfortable in these types of situations. That's achievable through using an HVLS fan or some other, comfort device to make sure that we're in that, 70 to 72 range. So there's pretty significant advantage to applying an HVLS fan for that occupant productivity and thermal comfort application. The other couple applications that I mentioned earlier that we'll spend some time on are a little bit lesser reason for using an HVLS fan, but we're starting to see more and more momentum here. And really probably the most important one outside of that thermal comfort application is reducing building costs. So I mentioned this earlier, but HVLS fans can be used to help offset the first cost of an HVAC system by either downsizing or reducing the need for other types of equipment in the project. So here's one example of how this can be done. HVLS fans can be used very effectively to downsize cooling equipment in a conditioned space by essentially just changing your indoor design conditions and using the HVLS fan to offset that temperature change. So I have an example from an actual application. This is a project that we had some fans added to in a CrossFit facility in Kentucky, where the facility was cooled to a 72-degree temperature set point, and they had about a 15-ton required cooling capacity, which meant that they were at about a 16-ton unit for the building. By adding the HVLS fans to their design, we were able to increase the temperature set point for the cooling equipment to 77 degrees and use the HVLS fans to provide that 5-degree roughly cooling offset from that perceived cooling effect of air movement across an occupant's skin. And as a result, we were able to downsize the unit for air conditioning to about a 14-ton unit. So that's a 2 tons savings in terms of unit sizing, which is a pretty significant first cost savings, and actually ended up being an offset of the cost of the HVLS fans. So there's a lot of opportunity to use the fans to, offset or change your design conditions and reduce equipment sizing. But there's also a pretty significant opportunity to just reduce the need for some of your ductwork or maybe your air distribution devices as well. So here's another example of how an HVLS fan was used in a real application to do this. Basically, the HVLS fans were used to provide air distribution in a large open floor plan office environment that was originally designed with 14 individual zones that each had a VAV system supplying air to them. Instead, the design team on this particular project was able to take those 14 zones and reduce them to 4 zones with the addition of the HVLS fans to distribute air in the space. And this ended up being about a 20% reduction in both material and labor by reducing the number of VAV boxes, the amount of ductwork, et cetera, that was required to install this particular system. So a lot of opportunity to kind of reduce or even eliminate the need for some of your HVAC equipment in these projects, just simply by taking advantage of, again, the air circulation capabilities of an HVLS fan. On top of that, those are all first cost savings. I mentioned earlier that HVLS fans can also be used for some operational savings, in particular, increasing building efficiency. So this kind of goes back again to the fan's ability to destratify or just reduce the need for cooling of a space. Because what we're able to do is, again, change our design conditions in that space. So in a cooling scenario, in a summer month, you can save upwards of about 30% on your cooling costs just by running the AC less frequently, or again, increasing your temperature set point in the space so that we're maintaining a higher temperature, but we're using the HVLS fans to help people feel like they're at that original design condition temperature. So this is very effective. And again, there is a free to use tool that the Center for the Built Environment has developed. Website link is on screen again, that can help you determine the savings potential from using an HVLS fan to offset that air conditioning cost. So they have it broken down by even, the fan cost, the cooling, equipment cost, your compressor savings cost, as well as, your reheat costs, et cetera. And really, really nice way to help, again, kind of maybe justify the use of an HVLS fan to help offset that cooling cost. Similarly, in the heating mode or heating season, HVLS fans, through that process of destratification, can help save about 30% on your heating costs just by conserving heat that's already in the building. So when you have that very large temperature differential from floor to ceiling in a space, that high temperature air at ceiling is typically, allowing heat to escape through the roof deck. And you're essentially wasting a lot of the heat that you paid for to put into that building. By just pushing that warm air back down to floor level and reducing, that temperature delta from floor to ceiling, we're able to conserve a lot more heat and, again, reduce the amount of heating that has to be done in that building just by recapturing that already heated air. So general rule of thumb here is there's about a 5% energy savings for every 1 degree that you're able to offset with an HVLS fan. So if you can offset, a 5, 10, 15 degree temperature delta from floor to ceiling, there's some pretty significant savings that can be achieved using this type of equipment, in addition to the rest of your HVAC system. I also touched on occupant health and safety earlier. This is another big application that, especially as of late with the COVID-19 pandemic, has started to gain more attention in our industry. But HVLS fans have, again, been studied and determined to improve not only the measured indoor air quality in a space, but also the perceived indoor air quality in a space based on occupant surveys. People, generally speaking, associate, air movement and a breeze with fresh air. It's, again, similar to being outside. When you have that breeze across your skin, you feel like it's a more fresh, better quality air that you're breathing. But there is also, again, a measurable impact from having an HVLS fan operating in a building in terms of indoor air quality. And the reason for that is, again, that the fan is able to kind of dispel those stagnant pockets of contaminated air in a space and get more, even distribution of those contaminants and particulates, as well as push that contaminated air to, discharges from fans or the rest of your HVAC system to actually exhaust that contaminated air more effectively. There have also been studies done. One was actually recently completed by AMCA, indicating that HVLS fans can help reduce the spread of airborne pathogens in a space by pushing that airborne pathogen out of the airstream and depositing it on surfaces. So again, that high volume air movement is effective at kind of pushing those contaminants down to surface level where they're deposited on a floor, maybe a desk, and they can be captured and eliminated by other cleaning protocols. So there's a lot of advantages in terms of indoor air quality. But another health benefit from this type of equipment is actually using the fan to help just deter pests from entering a space. So a lot of HVLS fans are applied basically to use as a kind of a simulated air curtain in outdoor environments or partially covered environments because they help keep insects away just from the nature of, again, that air movement. So here's an example on screen here. This is I think a Division A baseball stadium that has some fans installed under their covered awning for the fans in the stands to just help keep them comfortable and keep bugs away in the summer months. But there's also some advantages even indoor spaces to keeping birds, rodents, other small animals from coming into that space and nesting because the rotation of the blades and the reflectivity of the blades essentially just deters or kind of scares those small creatures from coming into that area. So we're actually seeing HVLS fans applied in a lot of airport terminals purely for that reason alone. It's a fully conditioned space, trying to keep passengers comfortable while they wait for their planes, but we want to make sure that birds aren't nesting in there and disrupting those passengers as they're waiting to catch their flight. So a lot of different use cases for health benefits as well. And then building safety side of things, HVLS fans are very effective at not only drying wet floors just by, again, increasing the evaporation rate of moisture, but at reducing the ability for condensation to occur on floors and surfaces. Just, again, simply by providing a lower temperature differential between those surfaces and the air above that surface. So we're able to help prevent some of those kind of common injuries that occur in buildings by applying an HVLS fan to really eliminate slips, trips, and falls, which are the leading cause of workers' comp claims, anywhere from 13 to 14 million per year that's spent on these types of claims, particularly in industrial facilities again. There's also some benefit to using an HVLS fan, which is ceiling suspended, in lieu of a traditional circulator fan that are pedestal mounted or floor mounted, just to get rid of the cords and another potential trip hazard of those circulator fans by having the fan up above, the occupied space. So some building safety benefits there as well. And then last but not least, I mentioned architectural design. Again, we're starting to see a lot more applications for HVLS fans where they're using the fan either to complement the architectural design of the space, like you see in the image on screen here, or to maybe add a wow factor or a focal point to the design of that space. And it's purely just an aesthetic feature, not even necessarily used as a functional element. This is something that we're starting to see more and more of, especially as this kind of more modern design aesthetic becomes more prevalent in buildings. So this is something for any architects in the audience or anybody who works at an architectural and engineering firm. This is something that you may start to see become a little bit more prevalent, especially in atriums or entryways to buildings where you have that first kind of initial impression of the space. So that kind of gives you a broad overview of some of the reasons you may use HVLS fans, where you might use them in your design. Now let's talk about how do you actually implement an HVLS fan as part of your design? How do you size them? What do you need to make sure you're specifying? And then last but not least, how do you actually pick a product to put on a fan schedule? So generally speaking, this is really the design process that we see used most often in the industry and that we recommend people use to make sure that they're getting a good HVLS fan selection and something that will satisfy all the needs of the project. So the process is pretty simple. It starts up front with just understanding the design of the building and what is the intended application. Are we trying to increase thermal comfort? Are we trying to keep pests away? Are we trying to, have some combination of condensation prevention and thermal comfort and building efficiency? Understanding up front what you're trying to accomplish, it sounds very simple and very basic, but that really does dictate a lot of selection decisions when it comes to this type of product, because it can impact how many fans you need, the size of the fan that you may need, etc. From there, looking at fan performance and the amount of airflow, the amount of air speed that's required for that application, and then how does that level of airflow affect or impact occupant comfort? Because at the end of the day, again, even if we're trying to just prevent condensation on the floor, we want to make sure we're not making somebody uncomfortable as they're in that space. Then from there, it's really a coordination effort to make sure that there's sufficient structure and clearance for the fans, that we are complying with codes and regulations. And last but not least, again, that we're satisfying, the aesthetic design of the building and what the architect is really looking for in that space. So we'll go into each of these in a little bit more detail. And then if, again, at the end of the presentation, you have specific questions on any part of this process, I'd be happy to address them at the end. So like I mentioned, first step in the process is really just understanding what is the building design and what is our intended use for the HVLS fans. Because this, again, really dictates our initial constraints, possibly our layout for the fans, and then some of the performance requirements that we need to make sure we're accounting for when we start looking at a fan selection. So some really important things to be aware of here, and some kind of general rules of thumb. I typically recommend that when you're looking at where to place an HVLS fan, focus on where the people in the space are, or where the problem that you're trying to address is located. So if you're having condensation on the floor in the back corner of a warehouse, that's really where we want to look at installing those fans and look at a layout that, make sure we're getting enough airflow to that back corner of the warehouse. Or in this example image that I have on screen here, this is another warehouse example. We have very, very densely packed, racking off to the right-hand side of the facility. Maybe it doesn't make sense to have a fan over those racking aisles because there's not a lot of occupants generally in the aisles, and there's so much density of products on the racks that it's going to disrupt airflow. So maybe we focus a little bit more on the area close to the receiving docks where occupants are generally present. You also want to look at, your floor plan openness, just how much space do you have below the fan where that air can kind of travel and run out across the floor. How high is your ceiling? That can affect the sizing of the fan that you may use. You don't, generally speaking, want to put a 4-foot diameter fan 60 feet up in the air because you're just not going to have enough airflow or enough throw to push that air down to ground level. And then the type of occupancy, is it occupied 24/7? Are we talking about just a few hours a day that this area of the building is occupied? All of those can dictate, where we're putting fans and how many fans we may need. And then again, whatever your application may be can also affect our performance requirements and how many fans are needed, depending on if the building is heated versus heated and cooled, if we're trying to control moisture, pests, improve building efficiency, so on and so forth. So this is really critical before you even really start looking at a layout to understand what it is that you're trying to accomplish. Then from there, again, fan performance is really the next step in determining an appropriate selection. So we really need to understand what are the critical performance criteria and what are our requirements for the given building type and application that we've identified. So when it comes to HVLS fan performance, there's really 4 primary metrics, not too dissimilar from other fans and other equipment that you're specifying today. The 4 major performance criteria are airflow, air speed, fan efficiency, and sound. HVLS fans being a little bit newer to the industry, hasn't historically been a lot of industry standards or regulations that could be used for this and for defining some of these performance criteria. But over the last several years, that has started to change, and we're starting to see more and more standards be developed. So for airflow, there is an AMCA standard that's available. It's AMCA 230, and there is an AMCA certification procedure that is available for that standard as well to provide you with third-party certified and verified performance information on this type of equipment. So that one is probably the most critical standard to be aware of for HVLS fans, because it does provide, a set of rules that all manufacturers should be testing to give repeatable and reliable data, as well as comparable data across different products and different manufacturers. And we'll talk about that in a little bit more detail in just a minute and why that's so important. Air speed is also very critical for these fans. Like we've talked about earlier in the presentation, air speed really dictates somebody's comfort level in a space. So there is a relatively new standard for testing and determining air speed, which is ASHRAE 216. Unfortunately, there is not currently a certification program available for this standard. So look for, on your submittals or any information from an HVLS fan manufacturer, look for something that says it was tested in accordance with or tested, per the procedures in ASHRAE 216. That's about as best as you can get for this type of data currently. But there will hopefully be some development on, a certification procedure to get third-party verification of data in the future. For fan efficiency, the standard is actually a federal regulation. So it's in the Code of Federal Regulations, Part 430. This is an efficiency metric and an efficiency test procedure that was defined by the Department of Energy and is a minimum requirement in order to be able to sell HVLS fans in the United States. So the metric that's used there is called CFEI, the Ceiling Fan Energy Index. It's very similar to the fan energy index, if you're familiar with that on other types of fan equipment. The only difference is that the requirements for HVLS fan are twofold. You have to have a minimum CFEI value of 1.0 at full speed and a minimum CFEI value of 1.31 at 40% speed. So as long as you meet those two minimum criteria, the product meets the minimum efficiency regulation and can be sold in the US. Again, no third-party certification available for this today, but look for, that CFEI value on your submittals, any literature that you come across, because that will tell you that it's been tested and is, compliant with the government regulation. And then sound, last but not least, AMCA 340 is a standard that's in development currently. So not actually used at this point in time to measure or catalog sound data, but in the future, when that standard is finalized and published, there will be a standard test procedure and a certification program available for HVLS sound. So big takeaway here, there's only one certification program available today, which is for airflow. All the rest of these are standards that are useful and should be used by a manufacturer to provide you data that is, again, repeatable and comparable. So when we're looking at these metrics, at these different performance criteria, we really want to make sure that we're satisfying whatever the needs are of the application based on these criteria. So if it's a commercial space, let's say, inside of a retail facility, sound and efficiency may be much more important and hold more weight than perhaps airflow or air speed in that particular application. Versus a warehouse where it's already loud and already, a little bit noisy, we may not care as much about sound, and we may be looking to put more weight on our air speed in that space. So I mentioned that the AMCA certification is very important for HVLS fans, and that I would address that a little bit more. And here's the reason why. Unfortunately, because there hasn't been an available standard for many years for HVLS fans prior to the development of AMCA 230, there is a history of some inaccurate performance information being distributed for these products. And really, it's at no fault to any manufacturer or anyone in the industry. There just wasn't a standard available that was reliable and repeatable. So there are products out there that are still advertising or still, promoting some of that inaccurate performance data. And what we've seen is that there are pretty large discrepancies between that advertised data, that historical data, so to speak, and the actual as tested data according to the AMCA standard. In many cases, it's upwards of about 30 to 35% lower actual performance than what that manufacturer is advertising. That's where, again, AMCA certification is so critical for this type of product. You want to make sure when you're looking at, two submittals for two different product lines, that the data is comparable, that, they were tested in the same manner and that they're held to the same rules, so that you can make an accurate determination of which product is better suited for your specific project. So look for AMCA certification on these fans. We'll come back to this a little bit later towards the end of the presentation. This is going to be especially critical, not only for comparative analysis, but in the future for code compliance and regulation compliance. So again, we'll come back to this, but this is really why that AMCA certification is so critical for these fans. And just for reference, here's comparison of a Greenheck product to this particular competitor product as tested according to the same standard. You know, when you look at the original advertised number, the Greenheck product looks like it performs to a lower level. But when we test them both to AMCA 230, there's quite a bit more airflow out of our fan compared to this particular manufacturer's fan. So next step in the design process, you know, we've identified our building type, our application, our performance requirements, and what we care about. Next step is really starting to look at, are we maintaining comfort in the space? So again, this is where that ASHRAE 55 standard comes into play, and where data, you know, from AMCA certified performance information, as well as you know, data from fans that have been tested according to that ASHRAE 216 standard for air speed. That's where that information comes into play with making sure that we are compliant with ASHRAE 55 and we're providing a thermally neutral or a comfortable space. This can also be used to define that cooling effect that somebody would experience based on those given variables that we talked about earlier, and can be used to help you determine how much to offset your cooling set point, et cetera, when you're applying an HVLS fan. So again, here's a screenshot of, you know, the output from that cooling effect calculation from our CAPS and eCAPS program. And at this point in the design process, this is where we start to get into a little bit of potentially iterative design. So we've identified building type, application, performance requirements, check occupant comfort, and we're a thermally, you know, cold or thermally warm environment. We might have to go back and relook at our layout, relook at our fan selection to determine how we get back to that more thermally neutral environment. After we've kind of determined, you know, performance, that we're providing a comfortable space, this starts to become more of a coordination exercise, like I mentioned before. So in the design phase, a lot of times we'll look at, you know, a layout for HVLS fans and come up with an ideal placement. Maybe it's a very symmetrical building, and we want to have the fans directly in the center of that space. Well, at this point in the game, when you start to look at actual placement of the fan, where is structure available? How much clearance do I have around the product? This is where you may have to start to deviate or change the design a little bit. This example on screen here, you know, our ideal placement would be directly in the center of the space, but our structure is available along this grid line. So we had to shift the fans a few feet to the northern side of the plan. Things like that start to become more critical once you've identified how many fans, what diameter, and your performance level for the space. There are a lot of clearance requirements for HVLS fans. I won't go into all of the details here, but just a few kind of quick things for you to be aware of. There are requirements for, you know, just safety clearances around the blades to make sure that we don't come into contact with an obstruction. There are clearance requirements to other fans, walls, other HVAC equipment, just to make sure we don't have any negative interaction between the airflow of the HVLS fan and other equipment or other parts of the building. And there are, you know, some clearance requirements to make sure that you're not creating some other sort of negative interaction in the space with lighting or, you know, some other building features. So for example, you want to make sure that you don't have an HVLS fan directly below a light source, because that can create what's called a strobe effect, or kind of a flickering of lights that can be disorienting to occupants in the space. So looking at all those clearance requirements can be a very critical part of the design process, and it may affect some of your fan sizing, fan quantity, and even sometimes placement, like I mentioned previously. So again, coordination is really critical at this point, coordinating not only with your design team, but also potentially with the architect, electrical engineers, whoever else may be affected by some of these changes in where a fan is located in a space. I referenced regulatory compliance a few times throughout the talk today, but this is another very critical factor in the design process. We have to make sure that the selected fans and the layout of those fans in the building complies with codes and standards that are available in the industry. The two probably most critical are NFPA standards that are adopted into fire code. These are NFPA 13 and NFPA 72. I put all of the direct text from the standards on screen here for reference, but I'll summarize them very high level. What these standards require is that the HVLS fan itself is sized and located so that it does not impact the flow of a sprinkler system in the event of a fire in a building, and that it does not impact the spread of fire in that fire event as well. So there are a lot of requirements here. The maximum fan size shall not exceed 24 feet. That's why, for the most part, that's the largest available size of an HVLS fan in our industry. The fans have to be centered between 4 adjacent sprinklers so that, again, we're not directly below a sprinkler and impeding its flow. We need to have a minimum of 3 feet of vertical clearance between the fan blades and the sprinkler deflector to make sure, again, that the blades are not impacting flow of that deflector. And the fan has to be interlocked with the fire alarm system to shut down so that we're not promoting the spread of fire in the building by adding air and airflow to that fire below the fans. So a lot of requirements there, but very, very critical for most applications that have sprinklers in the building. Some other code requirements for you to be aware of. I touched on this earlier when we were talking about the importance of AMCA certification. ASHRAE, the IMC, and the International Electrical Code are all looking in future revisions to implement requirements for HVLS fans to either be tested or certified to the AMCA 230 standard so that, again, repeatable and reliable performance data is available to you as you're making these design decisions. So ASHRAE 90.1, the 2019 version, requires that they are tested in accordance with AMCA 230. The 2021 version of IMC and IECC both require that the fans are tested and labeled or certified through AMCA 230 as well. So these, if you aren't on these versions of the codes yet or standards yet, these are coming down the pipeline for you in the near future. And it's important to make sure that you're aware that that AMCA certification will be a requirement in the near future. And then really, again, the last step of the process is just coordinating with architects to confirm that the fan meets, the aesthetic design requirements of the space. HVLS fans, generally speaking, are very customizable. There's a lot of options for colors, different types of finishes, whether it's shiny or matte finish, even different kind of wood grain patterns are available. So there's a lot of flexibility to adjust, the looks and the aesthetics of the fan to complement or kind of stand out away from the aesthetic design of the building. So again, coordinate with your architects and your, interior design the coworkers to make sure that you're complying with what they're looking for the aesthetic design of the fan. So that brings us to product selection. That design process that we just walked through, there's a lot of steps, a lot of things to consider, a lot of codes and regulations and standards that you need to make sure you're complying with. How do you make that easy? A lot of people, I think, underestimate HVLS fans and tend to think that they're very simple products that, you can just pick a 24-foot fan and put it in any space and it'll work just fine. But the reality is that, there are quite a few things that need to be accounted for, quite a few variables that affect fan performance and the ability to, achieve whatever your application is in a space. So how do you make that easy? And really, I think I've referenced this a few times today. The answer is software. So this is our version of a selection software that is free and available to you to use for selecting an HVLS fan. But there are lots of other manufacturers out there that have software platforms available for this type of product. And I'll speak specifically to our CAPS and eCAPS software. These are really designed to take the guesswork out of an HVLS fan selection and account for majority of that design process and all those variables that we addressed earlier, so that you don't have to be aware of them or really pay as much attention to them. We really try to take that burden off of you and guide you through the selection process and make it very simple. So this particular software, I'll speak again to CAPS and eCAPS, can really reduce the time and effort that it takes to make a good HVLS fan selection. And you can get to the point of scheduling fans in as little as 5 or 10 minutes just by following through, the prompts in the software and using this free to use tool to make those selections. So the way this works, and I could do a quick demo at the end if anybody's interested once we address questions. But basically, you enter in some very high level information about your space, about the application. Then from there, you can customize your fan selection with any specific requirements that you have. If you need an even or odd quantity of fans, if you want to limit the maximum operating speed of the fans, any performance requirements like a specific cooling effect that you're trying to achieve. You can enter all that information and customize that selection and then compare available systems that meet those needs. So it may be different quantities, different sizes of fans, even different models that you can compare and contrast to determine what achieves the end design goal that you're looking to accomplish. And then from there, you can save your selection, export cut sheets, AutoCAD drawings, Revit content, tons of information right there at your fingertips to, again, make this a very seamless and pain-free process to select an HVLS fan. So with that, I will now turn it over for some questions. And I think Tracy's going to come back on and help me address those questions today.